Hi everyone, my name is Carlos Rodriguez. I'm a PhD student of computer science at Universidad Nacional de Colombia. I belong to a research group on artificial life in the Computer Systems and Industrial Engineering Department. My advisor is the Professor Jonathan Gomez Perdomo, and I'm going to present some advances related to my dissertation proposal. My dissertation proposal is entitled A Self-Healing Model for Distributed Environments Based on Artificial Life Techniques. Thanks for watching. The goals for my dissertation are to propose a self-healing model based on artificial life techniques applicable to distributed systems. To achieve this general objective, I pretend to model distributed systems behavior using a simulated multi-agent environment with communication capabilities. The main requirements of simulation are scalability, accuracy, configurable, and to have reproducible results. The main idea of my simulation is I pretend to simulate classic distributed algorithms. In this fashion, a distributed system is defined as a collection of component units. In this case, I abstract this in the notion of a process, when each process has a set of neighbors, and the process can communicate with each other. Definition, a formal definition of a distributed system is as a set of processes, P sub 1, P sub 2, until P sub j, when P sub I is able to communicate with P sub j and nodes are connected by a communication channel. Communication is based in two main primitives, sending and receiving messages, and the buffer contains messages that have been sent to the process but not yet received. The main primitives, we can see here the main primitives is send a message M to a process Q. P sends this message M, and when the message is sent, the message M is stored in the buffer of the process Q. When Q receives this message, it means that the process takes this buffer and process this message into the buffer of Q. If the message is not received, some empty set and empty set is returned. I'm going to simulate distributed algorithms that compute a function of predicate. In this case, I'm modeling processes that are interconnected in a neighbor that I model as a graph. The function of predicate f is global, and each process has an input sub I and produce an output out sub I. In a global level, we can see them as two vectors, a vector of inputs, another vector of outputs, where input sub I is equal to the input of the process I. And the output in the position I is the output of the process I. The global output is equal to the computation of the function f given this input. As an example of problems, I have the problem of routing tables. The input of this problem is the identity of the process, in this case P sub I, and the output is the routing table for each process. For example, for this process P sub 2, we can see that by using the channel E7, we can reach the process P7 and process P sub 3. And by using the H0, we can reach the process P sub 9, P sub 5, P sub 6, P sub 4, and P sub 1. And by using the channel E4, we can reach the process P sub 8. The rules of behavior for this simulation are the following. All the processes obey the same rule of behaviors. I don't require the process exchange more information than needed. I don't have centralized control. The idea is that each process do not learn or get more information than necessary. I think in the framework of Reynolds, in this framework is a round-based framework, and communication channels are FIFO, because I'm using buffers. And each process sends message to each of its neighbors and receives information from them. You can see this traditional algorithm from the book of distributed systems of Michael Reynolds, which we identify three main stages. An initial stage where the input parameters are initialized. And while new information needs to be shared, they execute to process an asynchronous round in which They share the new information to the neighbors, and I receive a stage in which by each channel it receives information from the neighbors and compute what is the new information and return the output and the compute of the function. At the end, there are some synchronization tags and the process return the output to I. I take this process in a parallel way. So I'm modeling by using agents. In this case, I'm using the library of the Professor Gomez, and the agents are processed with the same rules of behavior. The network is defined as a graph. I'm using the Young library, and each agent has a mailbox. In this case, this is the FIFO buffer. It is possible to generate different random topologies. In this way, each process is modeled as an agent. Each process has sensor for messages and neighbor, has four internal variables, one for the new information and the output, and the information that is shared in each round, and the message kiwi. And as in the actions, I have to initialize parameters to send the information to neighbors. This is the asynchronous round, and to receive and evaluate the new output and update the output. As a difference with the Reinald framework, I'm executing asynchronous round and receive in parallel. If a message is received, the new message is registered by the sensor. The receive action is started. Otherwise, an asynchronous round is started, and in the round 0, the initialization is performed. We can see here the process is working. When a process turns into red, it means that the process is running. You can see the control board out for process 9 by using channel is1 can reach the process P4. For process 7, by using channel is7 can reach process 3, as we can see here. By using channel E4 can reach the process 2 and the process 6, and so on. This control board output registers the output for all the process. And we can see how it's computing this network topology. The interesting thing here is that I'm modeling this architecture in a simple way, because the only thing that I model for an agent is a hash table with properties and the number of the round that the agent is executing. As a process program that compute for answer of the initialization action, if the process receives a message, they return the action of receive message, else they return an asynchronous round. And we can see here how is the initialization part. In this specific case for the routing, in the receive station, we can see how is the computation of the new information and the returning of the output to the control board. And in the asynchronous round, we can see how new information is shared to the neighbors. As a feature work, I pretend to compute more global functions. This is like cutting edge graph, maximum, minimum, and merging of files. In this case, I pretend this code that is hard-coded for the routing problem. I pretend to model this into a language that allow definition of the inputs, outputs, and these kind of actions in simple computations for distributed systems, and to complete the tracer and to end the graphic interface of the control board. Thank you for watching.